Hello everyone and welcome to this video. Today we are going to see how to connect to the UCLA cluster Hoffman2 and how to submit first simulation. So for this you will need to use some commands, some terminal commands. I will show you how to do it using Mac. If you have a Windows laptop, then you will need to install a third-party software like for example Putty to be able to achieve the same thing. So if you have a Mac, there's a simple way to do that, which is to use the terminal command, which will come in your application pre-installed in Mac. And this will be used to connect to the UCLA cluster and to submit your simulation. So the first thing is to connect to the cluster. For this, you can use the SSH command. You have to just type SSH, then your login at hoffman2.idre.ucla.edu. Once done, it will ask you your password, and once you type your password, you will be connected. And here at this point, you are connected to the UCLA cluster. So everything you do at this point is executed on the cluster, not on your laptop anymore. The first thing is at this point you are connected to your files, your file system on the cluster. So how to view these files, how to navigate into those files. So here there is no graphical interface for this, so you will need to type some commands to be able to move from directory to directory, see the files, create new directories, delete, copy files, etc. So here the first command that you need to learn for this is to type ls as a list, which will list all the files in the present directory that you are working with. So here, once you connect to Hoffman2, you will first arrive into your home directory, which is the directory which contains all your files. So here you see different directory that I have on my account. If you want to create a new directory, which is typically what you will want to do to submit a new simulation, you will use the command mkdir, make directory, and then put the name of the directory that you want to create. For example, here I want to create a directory named demo, and this will create a new directory. So now if you list again the file, you see that the directory demo has been created to the list of directory. Now, how do you go to this directory? You can use the command cd, which is change directory, and type the name of directory that you want to go. And here now you see that you are now connected to this directory. You can use the ls command anymore, and here you see nothing because there is nothing in this new directory. The next step is to be able to transfer some files from your laptop to the Hoffman account. So for this I will show you an example. There are various ways you can do that. I will show you one way to do this using Mac, and one way to do this is to use the terminal commands as well. So the first thing is that you can use the terminal on your Mac in the very same way that you can use it on Hoffman. So for example, you can go to a given directory by using the command cd, change directory, and type the address of the directory that you want, and use ls to list the file in this directory. So for example, here I have some example file that I want to use to run a simulation. So those are files, input files that can be used with LAMMPS to simulate a silica glass. So what I want to do is to transfer those files from my laptop to the UCLA cluster account. So what I can do is to use the scp command, secure copy, which can be used to copy some files from my local laptop to the remote UCLA cluster account. And the way to do that is to type scp, and then you have to say what do you want to copy. So here I just want to copy everything. I want to copy those 4 input files. So I can use the command star, which means everything. Otherwise, I can also list the names of all the files one by one, which is the same, but star would just mean everything. Then you have to say where do you want to copy those files. So I want to copy those files on Hoffman. So I need to put first my login and to say that I want to put those files on a remote server, which is the Hoffman2 server. So I have to put the full address of the UCLA cluster. Then the last thing is I need to specify what is the name of the directory on your cluster account, on your Hoffman2 account, where I want to upload those files. So for this, I will use the command, I will use a dot, and then here I have to type the directory, the name of the directory on Hoffman2 where I want to put those files. So one easy way to do that is to go back here on your Hoffman account, and to see the address of the present directory that you are in, you can use the command pwd, which gives you the address of the present directory that you are working in. So you can then take this address here and copy paste it here, and this tells me that I want to copy those files on Hoffman and put them in this directory. Then it will ask you your password, and then it will transfer all those 4 files. Now if I go back to the UCLA cluster on the right, I am still in the demo directory. I can now list the files, and now I see that the 4 input file has been transferred to the UCLA cluster account. The next step is potentially to see what's inside those files and potentially make a few edits. So the first way you can do that is to use the command nano, which is a simple way to edit text files. For example, if you type nano.in.glass, it's a simple way to be able to see what is inside this in.glass text file and potentially to make a few changes. So here you have access to the text file. You can make some changes if you want, if there is anything to be changed. For example, here I can change this initial comment here. And once you are done editing your file, you see at the bottom of this screen here, you have a few comments, a few shortcuts that can be used to either exit, etc. So here what you will want to do is to save your file and exit. So you will use Control X on your keyboard to exit this file. It will ask you whether you want to save or not. So here I don't want to save, so I will just type N, and the results will not be changed. So the next step is sometimes it's very useful to be able to copy paste some files, or to move some files, or to rename some files. So for example, one way to rename files is to use the command mv, which is stands for move. So for example, if I want to rename the input file in.glass into something else, I can use mv, then type the name of the file that I want to move, and type the new name that I want to rename it with. So for example, I want to rename this in.glass file into in.glass2. So I type the command mv in.glass2. And now if I list the files again, the file has been renamed into in.glass2. So I will name it back the way it was. Okay, and now the file is back to its original name. I can use this command as well to move files from one directory to another. For example, I can move this, I can create a new directory. So I will use the command mkdir to create a test directory. Now I can move this in.glass file into the test directory. And now if I list the file, I see the new test directory, but the in.file is not here anymore. It has been moved in the test directory. So I will want to move this file back. So I can go into the test directory. I see if I list the file, there is only the in.glass file. So I can now move this file. And here I want to move it back to the parent directory. So the directory that came before the test directory. So I want to go back one step. So one way to do that is to say, I want to put that into the home directory, the directory that contains the test directory. So you need to go back one step in the directory scheme. So one way to do that is to use ... which means go back one step. So here I want to move this in.file file, and I want to move it into the parent directory. And here, if I do that, the file has disappeared from test. And if I go back, I can change the directory and go back to the parent directory by typing cd ... means parent directory. And here I am back in the demo directory. I list the file, the in.glass is back. The next thing I will want to do is, for example, to remove this test file that I just created, this test directory. So the way to remove, to delete a directory is to use the command rmdir, which is remove directory, and to type the name of this directory. So here, if I type rmdir test, I am removing the test directory. Again, if I list the file, now the directory has disappeared. The last thing that is useful to do is to copy one file into another. So for example, I can copy in.glass into in.glass2. Here now, if I list the file, I have now two input files, in.glass and in.glass2. Again, now I probably want to remove this new file that I've just created. So I can use the command, this time rm, which is to remove simple files, not directories. And I just have to type the name of the file that I want to remove. So for example, here, remove in.glass2. And in this case, the file has been removed. So you have to be careful with the rm command, because it will remove files. And if you remove a file, then it's lost forever. So you have to be very careful about when you are removing file, because those files cannot be recovered. Then the next step is how to submit this simulation. So here you have all the files ready. So we have all the input files. We have the a data file here. We have some files for the potential, and we have the main input file. So now I want to submit this simulation. The first way to do that is to use the command lamps.q. Lamps.q will activate a small script which will ask you a few questions about the simulation that you want to run, and then will offer you the possibility to submit this simulation. Again, you cannot directly run the simulation on Hoffman. What you need to do is to submit it. So you need to submit the simulation. Then the simulation will go to a queuing system. And as soon as some processors will be available for your simulation to run, then it will start running. So you need to submit the simulation rather than just directly run the simulation. Okay, so we will use first the command lamps.q. It will ask you a few questions about the simulation that you want to do. So first you will have to click enter. Here you have a few options to choose from. Here what we want to do is to build a new command file for LAMMPS. So we will use the command B. This is the option to submit a new simulation. Then the first question that is asked is to provide the name of the input file. So in this case, the name of the input file is in.glass. This is the name of the main input file where all the LAMMPS commands are provided. Next step is the script is asking you how much memory would you like to allocate to your simulation. So here you can choose different options. If you are simulating a very large system, for example, you might require a lot of memory, but usually you need to ask as little memory as possible, because if you ask for too much, it's likely you will have to wait for a lot of time in the queuing line before you are able to have your simulation run. So typically for the types of simulation that we are doing on LAMMPS, requesting 2048 megabytes is a good choice. Again, you can ask for more, but you might wait longer in the queuing line. If you ask for less, it's possible that your simulation will just stop if it runs out of memory. So you always have to make sure you ask enough memory for your simulation to be able to run. So here we'll just put 2048. The next step is to select how much time do you want to allocate to your simulation. So again here, this is the time that you request for your simulation to be able to run on the cluster. So you need to make sure you ask for enough time for your simulation to be able to finish before the time limit. On the other hand, the more time you ask, the longer you might have to wait in the queuing system, so the lower will be your priority. So you might have to wait longer in the queue. So it's always good to request a simulation time that is as low as possible. But on the other hand, you need to make sure your simulation can finish before the time limit. Otherwise, the time limit might be achieved before the simulation is done, and this will cause the simulation to instantly stop, even though it has not finished. So for example, you will probably lose some files if you do that, because the simulation would not have reached the end. So the final data file would not have been written. So here we will just ask for a simulation of 1 hour, which would not be enough for this simulation, but we'll just take this example of 1 hour so that the simulation can start fast enough. Then it's asking you if you want to use our resource group scores. So those cores are private cores for our group, and we typically only use those cores for long simulation, for example, that can require up to 2 weeks of computational time, or for simulation that are very urgent for us to finish, very important projects. So here, most of the time you will say no, because we keep those cores for special simulation. So if you need to use those cores, ask me and we can decide whether this is appropriate or not. But otherwise, you would just use no. Then asking you how much cores do you need to select for your simulation. Okay, so your simulation will not run on a single core. It will run on several cores to be able to run faster. So the more cores you select, the more processors you select, the faster your simulation will be, but the longer you will have to wait in the queuing system. On the other hand, if you ask for too many cores, at some point the efficiency of your simulation will decrease, because you will have to wait for the cores to communicate with each other, so you will lose some computational efficiency. So usually you will want to use either 8 or 16, which are typically good numbers, so that your simulation will be fast enough but remaining efficient, and you won't have to wait for too long into the queuing system. Typically 8 is a very efficient number. Here we will only ask for only one processor so that your simulation can start as soon as possible. Then it is asking you whether you want to submit the simulation now that it knows all the parameters about how much memory, how much time, how much processors you want. Then you can just click yes to submit your simulation now. Then this input file will just be submitted. Okay, and now it has been submitted. It is in the queuing line, and it will take a couple of minutes for this simulation to start. Then once you are done, you can use the command the type Q to exit this script. So now we can list the files. Now you need to keep track of your simulation to check, is it running? Is it still in the queuing system? How long do I have to wait for this simulation to start, to run, and to finish? So one way to do that is to use the command myjobs. This command is going to list all the simulation that you have presently either waiting or running on Hoffman. So here you see a list. In my case, I have two simulations. The first one is a simulation that is already running. You can see that because its state is R, which means running. So here you can see first the ID of this simulation, of this job. So this is a unique number that is attributed for every new job that you submit. Here you see the priority index. So here, the higher your priority, the lower the amount of time that you will wait in the queuing system. Here you see the name of the job that you submitted. This is the time at which your job was started, and here this is the node where your job is running. And here you have the number of processors, of course, that your job is taking. Here I have a second simulation, which is the simulation that I just submitted. Its state is QW. It means that it's still queuing. It's still in the queuing line. So here I can see again the ID of this simulation. So far the priority is 0 because the system has not processed this simulation yet. I see here the name of this simulation in.glass, and here is the time at which I submitted this simulation, and here is the number of processors. So I requested only one processor for this simulation. And you can keep repeating this command to check whether the simulation is running. So here now the simulation has started. You can see that now the state of this simulation is R. It's not QW anymore, so it's already running. So the simulation is starting. It is starting to execute the input file line by line and to create the corresponding output file. So now if I list what is in my directory, I see that some new files have been created. The first thing is this command file in.glass.cmd. This file is the submission file, so we can take a look inside it. This file is the file that contains everything that you requested for this simulation. So this file contains how much processors did you ask, how much memory, how much time, etc. If you want to resubmit the same simulation later, you can just use directly this input file. It contains all the information that you would have provided by after typing lamps.q, providing the number of cores that you want to use, the memory, etc. So here we'll just use Control X to exit. So here, what do we have? We have the log file. So let's take a look at the log file. The log file doesn't contain anything yet. The simulation is still running. We can use here, if we want to see the weight of those files, we can use the command ls-lh. And here, this will tell you the list of all the files that we have inside this directory, together with their weight here in kilobytes. So here we see that the output file is already being created. So one way to check the state of your simulation is to take a look at the output file as the simulation is running. But since the simulation is still running, it means that it's keep adding some new lines to the output file based on what it is doing. So one way we can keep track of what is going on in real time is to use the command tel-f. And this command tel-f is going to tell us what are the new lines that are added to a given file in real time. So for example, if you use 10-f in.glass.output, which is the output file that is being created, here we see that the simulation is still busy with the performing the initial energy minimization. So we can see that it has so far reached 200 steps. We can see here the first column is the number of steps that it has performed. Here it is providing some information every 100 steps. The second column here is the temperature, which is around 5000 Kelvin at this point. The third column is the potential energy. We see that here the potential energy is gradually decreasing. This is because we are performing an energy minimization at this point. The next column here is the pressure. So here we see that the pressure is quite high. This is because the volume is not appropriate for this high temperature. So you have a high pressure. Again, as a reminder, positive pressure means that the system is under compression. Here you have the volume. Here the volume is expressed in cubic angstrom. This is because in this case we are using the real units. So all units of distance are expressed in angstrom. All units of volume are expressed in cubic angstrom. The next thing here is Lx, which is the size of the box on the x-axis. So here we have a box that is a cube, which has an edge of 35. You see that a new line just has been created, added to the output file. This is because the simulation is still running. So as it is running, we will see those files appearing by using the tail -f. Every time a new line is added to the output file, it will just appear on the screen. And then the last thing is the density. So here the simulation has finished the initial minimization. Here you can see some information about the energy minimization and why it converged, etc. Here you can find some information about the computing time. So here you can see that it took, for example, 220 seconds on one processor to finish those 300 steps of energy minimization. You can find here some more information about exactly why this time, what is the different origin of the computing time. For example, here you see that almost 20% of the time was used to calculate the interaction energy between each pair of atoms. 80% of the time was used to calculate the long-range Coulombic interaction. 0.2% of the time was used to calculate the neighbor. You have a small percent, less than 0.1%, that was used for communication time. So this is typically something you need to check. If the communication time is very high, it means that most likely there is something wrong with your simulation. Maybe you are asking for too many processors, so they keep communicating with each other. You are losing some computing efficiency. Here, this is the output time. This is the time that it takes to create all the output file. So here you need to make sure that this number is always very small. If this number becomes very high, it means that the simulation keeps writing new files. It means that most likely you are writing the output file too often. You might want to decrease the frequency at which you are writing the dump file or the output file. And then the last category is any other time that was used by LAMMPS for the simulation. So usually, if everything is fine, most of the time should be spent to calculate the pair energy between each pair of atoms and the long-range Coulombic interaction, which is the k-space time in this case. So the simulation is still continuing. Here it is starting to perform the initial NVT simulation. We see that the temperature is changing, the energy is changing, but we are in NVT ensemble, so the volume is fixed, so the volume is not changing, and the size of the box is also not changing. Okay, so once you are sure that the simulation has started, so here it's going to take a long time for this simulation to finish, so we'll just have to wait. So the first thing is to exit this tel -f commands to stop watching what is written in the output file. You can use Control C to exit this file, and here again, going back to the directory where the simulation is running, you can list the file to see what has been created. The other file that has been created is the dump file, md.lamps trj, which is the LAMMPS trajectory, We can take a quick look at it by using the command nano, for example, nano md.lamps trajectory. So here we see the typical trajectory file, which contains the current time step, the number of atoms, the size of the box, x low, x high, and then for each atom, its ID, step, and its position, x, y, z. Those are here all the position of the atoms that we will have according to time. Okay, you can type Control X to exit this thing. So here the simulation will just continue, and it will take most likely around 8 hours to finish if you choose around 16 processors. In this case, I choose only one processor, one core, and only 1 hour. So the simulation will just stop before it has the chance to finish. A few other comments that are useful and that you need to remember is that if you type myjobs, so you see the list of all the simulations that are running. If you want to stop one simulation because you see that there is something wrong, for example, you can type the command qdel and then put the ID of the simulation that you want to finish. So for example, if I want to delete this LAMMPS simulation that I just started, I can just type qdel and then copy paste the ID. And this will kill this simulation that is going to be deleted. So now if I type the myjobs command, you can see that this simulation has disappeared. It has been deleted. Another command that is useful is if you want to look for a given file. So for example, let's assume that you run a simulation with a given ID and you forgot where this simulation is running, in which directory is it running. So you can, for example, go back to your home directory, which can be achieved by just typing cd, so change directory with nothing else, will bring you back to your home directory. And then one way to look for a given file is to use the command find. So for example, here I'm going to say I want to find all the file that contains this specific ID. So that will be a way to locate where is this simulation running. So I want to say, okay, I want to find, you have to say where are you going to try to find those files. And here I'm going to use just dot. Dot means present directory. So double dot means the parent directory. Dot means the present directory. So here I am in the home directory. I want to look everywhere in the home directory. So I want to use the dot to say I want to look everywhere for this file. And I'm going to type minus name. So I want to look for files according to their names. And I'm going to look for files that have a name that contains this ID of the simulation that is running to see where is it running. So one way to look for files, I want to look for files that contain this ID in their name. So I'm going to use the command star before and after this ID. It means that I look for every single file name that contain this ID. So the name of the file can be anything. So anything means is denoted by this star. So the name of the file can contain anything, then can contain the name of this ID, and then can contain anything or nothing after that. So star can means anything. So then I'm looking for this file. So let's see what is found. So I have a lot of files on my Hoffman account, so it might take a few seconds to find. So let's see. And here it has found two files, which are the output file and the log file. So this means that here in this directory, this is where this simulation is running. So this is useful if you have lost a file somewhere. You can look for it where it is by looking based on its name, where is it inside your home directory. Another command that is very useful is to look for how much free space do you have on your home directory on Hoffman. You have to be very careful with that. There is a limit of 20 gigabytes on your Hoffman account, and if you reach that limit, then all your simulation will stop because you won't be able to write any new file. So the way to check how much space is presently used on your account, on your home directory, is to use the command du-sh. So you have to go first onto your home directory, type this command du-sh, and then it will tell you the size of all the files that you have in your home directory. So in this case, I am already using 18 gigabytes. So you have to be careful that if you are getting close to 20 gigabytes, you need to clean up some space by transferring some files back to your computer to save up some space from Hoffman. So one way to take some files from Hoffman and to put it back on your laptop is to use again the scp command. For example, here I want to take some of the output file that have been generated. So here I stopped the simulation, so it's not complete yet, but I can still use this output file to start looking at it if I want to. So if I want to take this output file and put it back on my laptop, what I can do is go back here, which is my local laptop, and use the scp command to this time copy some files from Hoffman to my laptop. So the way that would work is to type scp. What do I want to copy? This time I want to copy some files from Hoffman to my laptop. So I will type my login at hoffman2.idre.ucla.edu. Again, ... Here I have to put the address of the directory where I want to copy files from, and here I want to copy this output file. So I will copy the name of this output file here, and I want to copy this file on my local computer. So again, I want to copy in the present directory, so I will just use the dot to say I want to copy it here. Okay, dot means here. Again, it will ask you for your password, and now you have this new output file that has been transferred onto your laptop, which you can edit or view using a text file, or you can take this file and start to look at the thermodynamical properties of your system by looking at the information contained into the output file. Okay, so I hope this video was useful. We will see more videos about how to use Hoffman, how to better analyze the types of output files that are created by the simulation. But this is the basics of how to connect to Hoffman and how to submit a new simulation and see how is it running and how long has it been running so far. Thank you for watching.